Okay, let's talk about charges just moving through space. So instead of defining our motion with a current and a length, let's talk about just charge and velocity this time. So our current is a collection of charges, and those charges can occur in a wire or they can just move through the air, kind of like Ghostbusters in the proton packs. So we know in the moving through the wire, we define it as Bill sine theta. That was the force, the magnetic force. B is the B field, I is the current, L is the length in the magnetic field, and theta is the acute angle between the length of the wire and the magnetic field. Well, if I want to look at this a little bit differently as charges through space, I may not know the current. So I can look at this and say, well, I, that's the current, is equal to the charge divided by the time. And I can make a substitution for I in the formula. So now, instead of Bill sine theta, it becomes BQL sine theta divided by T. And now I can make it look a little different and slide the T over, so it's still in the denominator of the entire equation. But L over T, well, that looks like the velocity. So now with this, I can substitute in for velocity, and I get a new formula. The magnetic force is also equal to qvBsin theta. So this describes the force felt on a charge in an external magnetic field. What's different about this equation from our other one is instead of defining it with current and length, I'm defining it with charge and velocity. So it just gives me a second way of finding that magnetic force. And this works for charges moving through a wire or just charges moving in the air, like say a lightning strike.